With polar equations, we certainly could keep on picking theta, calculating r, picking theta, calculating r, and then using the knowledge that anything with a cosine in the equation is going to be symmetrical with respect to the horizontal polar axis. And anything with sine in the equation is going to be symmetrical with respect to the vertical theta equals pi over 2 axis. We could keep on doing that. It's a labor-intensive, time-taking undertaking. It's a time-intensive, labor-intensive undertaking. So that's why it behooves us to learn something about special polar graphs so that we can identify them. So the equivalent of this in rectangular form is that when I give you y equals x, you know right away it's a graph like this. Now, you could pick x, get y, pick x, get y, and get all of these points. But if you know what it looks like, you can quickly graph it. Or y equals x squared. You know it goes through 0, 0, 1, 1, 2, 4. And it's going to look like this. Or y equals x, which is a V shape. Or y equals the square root of x, which you know looks like the swimmer function. And you could certainly pick x and get y, but here we'd have a restriction on the domain that the x's we pick should be greater than or equal to 0. We get that 0, 0 point. And of course, from this year, y equals sine x, y equals cosine x, etc. If you know what they look like, you're so much quicker at graphing them, be it a sketch or a detailed graph. We're going to start this process by looking at Limacons? No. Let's fix this and put the cedilla here. Limacons. Limacons are of the form r equals a plus b cosine theta. Now, I could make this, it's really r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. What's important for us to note, first and foremost, is terms are separated by pluses and minuses. So here I have two terms in each of these. I have two terms. As soon as I see two terms, mara moja, as we say in Swahili, immediately I know I must be dealing with Limacons. Two terms, Limacons. Two terms, Limacons. One more time. Two terms, you have a Limacon. So here I see a plus b cosine theta. Because I have two terms, I know it's a Limacon. Now, we have 4 flavors of Limacons. Once you open the Limacon door, inside you're going to have 4 different flavors. The first flavor is when A is less than B. And I can draw a sketch of that. When A is less than B, we're going to have a Limacon with an inner loop. And it looks something like that. Notice it's going to go through the pole, and I'm going to go out to this point, to the outer loop. Well, the furthest distance, I'm just talking r, I'm not talking the angle. The furthest distance away will be a plus b, whatever's here plus whatever's there. The inner loop will be a minus b, or take the difference and then make it positive, absolute value. It goes to the pole, and now the free-floating number is a. I'm going to go up a and down a. Now, if this point might be something like a comma 3 pi over 2, and this point might be a comma pi over 2. Why do I mention that? Because I want you to stop thinking in terms of x and y. This is directed distance, directed angle, directed distance, directed angle. And of course, this would be a plus b, that's the distance r, and the angle is 0 radians, etc., etc., etc. All right, so there is a is less than b. Continuing along, a is equal to b. Well, because it's a positive cosine function, cosine means we're going to have, for this last one, we have polar axis symmetry. Whatever's on the top will be on the bottom. When a is equal to b, we have this shape here. This one is called a cardioid. Notice, cardioid, brings to mind heart shape. This here, to get out here, we're going to have a plus b. I'm just talking about the distance r, directed distance r would be a plus b. Here is a, and here is a. Notice I'm not saying negative a, because I'm not thinking in terms of rectangular coordinates anymore. And that is going to go through the pole. Notice here, I mentioned this, but I did not write it. This is a limacon with, we say it's with an inner loop. So notice the inner loop got pulled out, almost like you got a dent in your car. When A is less than B, you just got a dent in your car on a Friday night. Now you make A bigger to be equal to B, and you have one of those little suction cups for doing your own home auto body repair, and you pull the dent out a little bit. Will mom notice that dent come Saturday morning? Oh, she will. Good thing she's out for the weekend. You still have time to work on that dent. Well, you're increasing A. So if we increase the power of A and say A is bigger than B, then our limacon is going to look like this. Almost like a lima bean. It's a limacon. We say this is a limacon that is dimpled. So we call it the dimpled limacon. So I'm writing limacon, but I should be writing dimpled. This is a dimpled limacon. Which is interesting because that was my nickname back in high school. I had these beautiful little dimples. People were crazy for me back then. You should have seen me. I was something. So, well, what is this? We're going to go out A plus B here. And of course, similar to this inner loop, we're going to have A minus B absolute value, and we're up A and we're down A. Note, this looks like a lima bean. It's going to slightly pull in. And that's when A is just a little bit bigger than B. If A gets a lot bigger than B, so I know this is not correct math terminology, but I'm showing you A is a lot bigger than B. So what do I mean by that? Well, A over B is greater or equal to 2 over 1. So A has to be double B, at least double B. Then we're going to have kind of this egg on a table kind of shape. See, if this was the table here and this was gravity pulling it down, it's going to look kind of like an egg on a table. This is A plus B for R. Again, the backside here is A minus B, absolute value, and we're going to be here and here at A. So if you crash your car or you have a little fender bender on a Friday night, your parents are gone for the weekend, and you go get your own home auto body repair kit, A is small. We want to pull that dent out. So what do? Bump A up. It's equal. Would mom still notice that? Yes. So keep on bumping A up. Now we're pulling that dent out by making A bigger and bigger and bigger. And when A is so much bigger than B, we've pulled it out, we've sanded it up. Mom comes home, we give her the keys, and she says, "Hey, little Johnny," or "Hey, little Susie, how did things go?" She takes a look at the car. She'd never noticed the difference there. A small, inner loop. By the time A gets much bigger than B, it's nice and sanded and smooth. And the process of evolution, as A gets bigger than B, you can see here. One of the things I've seen, students don't hang these buns. If you think of these as nice rounded buns, they forget to put these buns hanging over the edge. So don't be afraid. In life or with limacons, don't be afraid to hang those buns out. That first example I did was A plus B cosine theta. Now look at this limacon. How do I know it's a limacon? Immediately, two terms. A minus B cosine theta. It points to the left. The majority of the graph is pointing over here to the angle of pi. So A plus B, A minus B absolute value. It goes to the pole, and A hanging the buns over. Same thing here. The cardioid has these buns above the pole, or to the right of the pole in this case. A and A plus B. Now, A minus B absolute value was the inner loop. Now it's the backside of the dimpled limacon. And here we keep that the same for the convex limacon. And A plus B, A and A. By the way, I forgot to say, this one is known as the convex limacon. That's the difference. If A gets much bigger than B, it's called a convex limacon. for this particular polar equation, I have two terms. Immediately, Maramoja, I know it's a Limacon. Now, what flavor of Limacon depends on A and B. It's a positive sine graph. As soon as I see sine, from all of our work, you know we have theta equals pi over 2 symmetry. For each of these graphs, the left side is going to be mirrored by the right side across this vertical axis, which we no longer call the y-axis. In polar form, it's going to be the theta equals pi over 2 axis. Notice everything else is the same from what we did with the cosine. A and A for your polar axis intercepts. It's going to go through the pole. A minus B absolute value will give you your inner loop, and your outer loop will be A plus B. I'm talking about the R. I haven't mentioned theta, but of course you could guess that this angle is pi over 2, and this might be 3 pi over 2 as long as R is negative. I hope that makes sense to you. Look at, we're hanging the buns below this polar axis. Here, the parts of the heart, if you want to call these buns again, they're hanging below, and it goes through the pole. Our dimpled Limacon, A minus B on the back side with the absolute value, A and A plus B. And when we get A much bigger than B, so we're saying that the ratio of A over B is greater than or equal to 2 over 1, then we're going to have this convex, looks like an egg sitting on a counter, to me anyways. Maybe that's because I'm always looking for something with protein in it. This here will be A minus B absolute value. And there was something else I was going to say about that, but there it is. Beautiful. Convex Limacon. Our final option here is R equals A minus B sine theta. Immediately, I know two terms must be a Limacon. It's a negative sign, so it points down. Because it's sine, I have this theta equals pi over 2 symmetry. Once I know it's two terms Limacon, I compare A and B. What flavor of Limacon is it? If A is less than B, then I'll have an inner loop. If A is equal to B, I've got this cardioid. If A is a little bit bigger than B, I've got this dimpled Limacon. And if A is at least 2 to 1, greater or equal to 2 to 1, A over B, then I'm going to have this egg shape. It's pointing down now. And all of the rules of engagement that we talked about before are going to be true here to get this back point as well. We've talked about those before. I'll let you look at those.